Hey everyone, I would like to thank you for attending our tutorial on big sequence management, scaling up and out. So in this tutorial, we will talk about how to efficiently manage and do complex analytics on top of very large collections of sequences or data series or time series. We will focus on techniques, on recent techniques that have been developed in this area that take advantage of modern hardware parallelization and distribution. And finally, we will also talk about the relationship of this area with general high dimensional vectors and how these techniques can help us in that case as well. So for example, with the analysis of large collections of deep network embeddings. So this tutorial is delivered by Karima Echihabi from Mohammed VI Polytechnic University, Kostas Zoumpatianos from Snowflake Computing, and myself, Themis Palpanas, from the University of Paris and the French University Institute. I would like, first of all, to thank all the people that have contributed with slides, and especially the authors of different papers that have shared their slides with us to include in this tutorial. So data series are nothing else but a sequence of points ordered along some dimension, the x-axis, and when this dimension can be several different measures. So when this dimension is time, we call them time series. But the x-axis can also be other dimensions like angle, position, mass, frequency, and others. So I will spend a few minutes at the beginning to give you some examples of applications in all these cases. So of course, most of us are familiar with time series, and time series exist in several different domains and applications, ranging from meteorology, oceanography, to astronomy, finance, and sociology. So, so the two examples on this slide come from wind speed measurements over time, and from historical stock quotes on the right. So this is an example where we have a time series measuring the amount of bandwidth consumed by different users over time. And in this case, doing usage behavior analysis using time series data allow us to have a more accurate picture of how bandwidth is used, irrespective of the demographics of the users. And this is very useful for telecommunication companies, and of course the design of their networks and also marketing campaigns. And now some examples that may not be immediately obvious that are related to data series management. So one comes from neuroscience. So in neuroscience, one of the key tools that they use for their experiments is the functional resonance magnetic imaging data, fMRI. So this is the primary experimental tool that allows neuroscientists to test how different parts of the brain respond to different stimuli. So neuroscientists are people that take great pleasure in putting other people in these big machines, and then they provide them some stimulus, and then this machine measures the amount of blood flow over time in different parts of the brain. Now, this amount of blood flow can be translated into a time series whose analysis can tell us, can reveal us information about the functioning of the brain. In entomology, entomologists are very keen on studying different insects, especially those that invade agricultural crops. One way of doing this is by fitting this small electrical circuit around this insect, transforming the voltage difference into a time series. And then by studying databases of such series, we can understand what is the type of the insect, the sex of the insect, and even the kind of behavior that the insect is involved in. So, for example, feeding from a plant. Now, an example where the x-axis is angle comes from astrophysics. So, in this case, we're interested in studying the chemical compound profiles for different stars in the universe, and this is what reveals us information about the composition of these stars. An example where the x-axis is position comes from biology and genome sequences. So this is an example of the first 100,000 bases of some genome. We can do the same for a different genome, and then we can try to identify whether there are some subsequences in one genome similar to any subsequence in some other genome. An example where the x-axis is mass comes from mass spectroscopy, and in this case we're trying to compare normal and malignant cancerous ovarian cells, and we can do the same also by using infrared spectroscopy, in which case the x-axis is frequency. In this example, we're also talking about ovarian cancer cells. So, apart from all these scientific applications, we also have applications that come from IoT, and you can think about all these big production control systems that we now have in place, monitoring different machines and production processes. So all these, they produce time series that need to be analyzed. And of course, the same is true for vehicle operation monitoring. So modern cars and even more importantly, planes are fitted with thousands of these kind of sensors, and we need to analyze this kind of data in order to test whether the operation is normal or not. And of course, we can observe now at the level of detail that is unprecedented our environment, so different aspects of our environment, including how our world, how the Earth behaves. So, for example, through seismometers. And once again, all these applications, they produce large amounts of time series that need to be analyzed. Now, one important point here is the discussion about treating a set of points, treating a collection of points as a set or as a sequence. You may think about the streaming data. So, for example, the IoT applications that I mentioned earlier. So, in this case, even when we have streaming data, usually we always talk about a window of interest. So, for example, I'm only interested in what has happened in the past 1 month or in the past 5 minutes. Now, the data points inside this window of interest can be treated either as a set or as a sequence. And it makes a huge difference what choice we make. So, for example, in anomaly detection, it may be the case that we observe some anomalous behavior if we look at the points in our window of interest as a sequence. So in this case, the order of the points is important, and we can actually see the trends and see this sudden drop that is observed here, which is anomalous. Or we can treat the same points as a set, in which case we can measure what is the distribution that these points exhibit. And it may be the case that this distribution is well within the minimal and maximum thresholds specified by the experts. So if we treat points, the points inside our window of interest as a set, we may not be able to discover that there is something wrong going on. On the other hand, if we treat them as a sequence, then the trend itself reveals something anomalous. So it's very important to treat time series as sequences, because the ordering of the points conveys more information than treating them as a set. Now, there is, of course, lots of work that has been done on data series signal processing, and there is lots of work on different problems related to, for example, periodicity detection, modeling and forecasting, point outlier detection, where we focus on the single next value. So we will not talk about these problems. We will instead focus on sequences as first-class citizens and very large collections of series. So how we can apply fast and scalable similarity search for sequences or subsequences, which is what can actually drive in an efficient way more complex analytics, as we will discuss later on. So the objectives of this tutorial is to introduce the data series type, its characteristics and properties, and we will talk about very briefly about data series representations, about data series similarity matching and indexing. We will briefly discuss different systems for data series management, and then spend some time discussing different challenges and open problems. So in terms of data series representations, there is lots of work that has been done on how we can actually represent and oftentimes summarize sequences or subsequences. So these techniques are used both for representation and storage of data series, and they also drive other more complex data structures like indexes that we want to build on top of data series. So the main goal here with all these data series representations, summarizations, is to actually summarize the data series, so reduce their dimensionality, and consequently render the subsequent processing more efficient. So let's start by some basic notions. So, like we said, a data series is a sequence of points ordered along some dimension, and we will use interchangeably the terms data series, time series, data sequence, or sequence. The number of data series values is called the length or the dimensionality of the data series. Usually, if we have a series where each point is actually a multidimensional point, then we call this series multivariate data series. A subsequence is a subset of continuous values of some series. So in this case, this box specifies a subsequence of length 4. Now, when we want to compute the distance between two data series, for example, the red and the blue, one simple way of defining this is by considering all the pairwise distances, and for example, Euclidean distance between all these points. This is also the reconstruction error if we assume that, for example, the blue series is the original series, and the red series is the reconstruction of the original based on some summarization. So let's now see why we want to use these representations, summarizations, and how they can actually help us. So when we have large collections of data series, what we want to do is answer queries. And there are two kinds of queries. So one type is what we call simple queries. And this involves queries like, for example, give me all the values of series with ID number 5, or give me all the values within this time interval, or give me only the values above some threshold. Now, these are, if you think about it, select project queries. And these queries can actually be answered relatively efficiently using your favorite data management system. Well, actually, as we will talk later on, there are still some challenges and open problems in this area as well. But even more importantly, what we want to do with these large collections of data series is to perform some complex analytics tasks. So answer more complex queries. So for example, classification, clustering, outliers, motifs, frequent patterns, your favorite mining or machine learning algorithm. In all these cases, once again, what we want to do is to analyze the evolution of values across the X dimension. So treat these points as this sequence of points as first-class citizens, and look at the trends that these sequences correspond to. So even in the case where we talk about data series that have a very that are very long or have an infinite length, so streaming series, even in these cases, we're interested in small subsequences of these series. So, for example, the patterns of interest. If we talk about cardiologists, are a single heartbeat. So even if we have a very long series of heartbeats, what we want to make sure is that every single heartbeat is normal. So in this case, what we do is that we can chop a very long or infinite sequence in subsequences that have a length that is sufficient to cover the pattern of interest, and then we process these subsequences. So going back to this picture, in all these different cases where we have complex analytics, one common denominator is similarity search. So for example, think about KNN classification, where we assign a new label based on the nearest neighbors of the new subsequence. So this is a similarity search operation. And similarly, similarity search is important for all these different other complex analytics tasks. But doing similarity search in this context is very hard for two main reasons. One is the very high dimensionality of the data series. So each data series may contain hundreds or thousands of points. And second, because our collections can grow very large very quickly. So in several cases, we have collections that have several hundreds of millions or even billions of data series, which translates to collections multi-terabytes in size. So we will talk later on in this tutorial on how we can actually efficiently manage such collections. Let me just spend a few minutes now talking about some pre-processing tasks and introducing you the data series representation techniques. So in terms of pre-processing, something that is very usual and very important is Z normalization. So Remember that when we talk about data series analysis, we're interested in identifying trends and similar trends in data series. But in some cases, the absolute values may or may not be important when we want to compute this kind of similarity. So, for example, these two series, they follow the same trends. They go up and down and then up again, but their distance is pretty large. What we can do is to Z normalize these two series. This means that we make sure that they both have a zero mean and also a standard deviation of 1. And after we make these adjustments, so both the blue and the red series, they have a zero mean and a standard deviation of 1. They are both Z normalized. Then their distance is very small. So this means that after Z normalization, it's easy, in this case for Euclidean distance, to identify that these two series are very similar. They have the similar trends. As I just mentioned, we want to Z normalize when we're interested in the trends, not in the absolute values. And if we're interested in the absolute values, this happens in some applications, then we should not, of course, Z normalize. Now, in terms of data series representation techniques, there has been lots of work that has been done in the past years. There are literally dozens of summarization techniques that have been proposed. So on this slide, I'm mentioning just some of them, and these are among the most prominent representation techniques. So starting from the left, it's the discrete Fourier transform that summarizes data series by using the most important Fourier coefficients of the series. So the most important frequencies that appear in the signal. Discrete wavelet transform, in this case with the Haar basis function. So this is a technique that is very widely used, also in several communities other than time series as well. Piecewise aggregate approximation basically summarizes series with a set of constant segments. Adaptive PCA does the same, but in this case, we have segments of different lengths, while in PAA, all the segments have the same length. PLA is piecewise linear approximation. So we have different linear segments to summarize, to represent our original series. And symbolic aggregate approximation is very similar to PAA, with the difference that after we have the PAA representation, we then represent each segment of the PAA with some symbol. So the way that the reason why we want to do this is because it's much it's because symbols take much smaller, much less memory to represent than the real values that we need for each segment for PAA. So we will not get into more details on all these representations. So there exist several previous tutorials that discuss all these points very well. What I would just like to say here is how these different representations compare to one another, and which representation is the best to use. So the answer to this question depends on the data characteristics. So whether the data are periodic or smooth, they are spiky, and so on and so forth. Overall, previous studies have shown that when we average the results over several different diverse datasets using the same memory budget, it makes no big difference which method we use to summarize our data series. However, it turns out that DFT, Fourier, piecewise constant approximation, piecewise aggregate approximation, discrete wavelet transform with the higher basis functions, and the symbolic aggregate approximation performs slightly better than others, on average overall. But of course, once again, if your data set have some specific characteristics, then maybe one technique or another may perform better. However, one last point here is that what we should take into account when choosing our representation method are other factors as well. So, for example, how well it visualizes, if we want to use visualizations, or whether this technique is amenable to indexing. And we will discuss later on why indexing depends on these summarizations. So if you have any questions, we'll be glad to answer them now.
We will now cover the query answering process of the data series similarity search. Query answering process consisting of two procedures, the data loading procedure and the query answering procedure. For big data exploration, it is prohibitive to fully scan the dataset for every single query. That's why indexes are built, to reduce the data to query time. Once an index is built, it needs to be loaded and queries need to be run efficiently. So both the data to query and query answering times are big, and we need solutions for both problems. One possible solution to improve the query answering time is by reducing the cost of the distance computations, because these can significantly slow down processes because of the large number of data series in the collection and the high dimensionality of each data series. In the case of the Euclidean distance, we can speed up processing by a smart implementation of the distance function and early abandoning. Both result in significant performance improvements. A smart implementation of the distance function consists of avoiding to calculate the square root of the distance. This does not alter the result and saves precious CPU cycles. Another technique can be implemented, which is called early abandoning. And it basically stops the distance computation as soon as it exceeds the BSF. And again, this does not alter the result and it avoids useless computations. One way of reducing the I/O cost of the query answering process is by building indexes. And most of the indexes in the data series literature are based on a framework called the Gemini framework. In this framework, the raw data, which is in a high dimensional space, is represented in a low dimensional space, and search is performed in the low dimensional space because it is less costly. But to guarantee that the results are correct and exact, and that there are no false dismissals, a lower bounding property is exploited. Lower bounding means that the distance in the reduced space between two points is guaranteed to be always smaller than or equal to their distance in the high dimensional space. So the closer the lower bounding distance to the actual one, the better. And we will see right now different classes of methods, and some of which are built on this Gemini framework. So the most simple solution to the similarity search problem is the serial scan. Given the dataset represented here by this gray oval, the points with the blue dots, the data fitting in on disk, and when a query arrives, query has to be compared to each row candidate in the dataset before returning the exact answer, which is CX. So we start by initializing a BSF to plus infinity. We calculate the distance between Q and the first candidate. Because it is certainly smaller than plus infinity, we update the BSF. And then we proceed sequentially, checking every single candidate in the dataset. Once the algorithm gets to the actual answer, the BSF is updated again. But the algorithm does not stop here. The exact algorithms, they have to process every single point before returning the final answer. And as you can see, for big data collections, this can be extremely slow. So an alternative technique has been proposed, and it's called skip sequential scan. In this skip sequential scan method, not all the points in the raw data are checked. The raw data is summarized, the summaries fit in memory, and they are organized in the same order as the high-dimensional data. So these techniques exploit the row bounding property that we have just seen in the Gemini framework, which guarantees that the distance in the low-dimensional space is smaller than or equal to the distance in the original space. We start with a BSF of plus infinity and a lower bounding distance also of plus infinity. We calculate the summary of Q, and then we calculate the distance in this summarized space between Q prime and the summary of the first candidate, C1 prime. If this distance is smaller than the current BSF, then this means that we cannot prune this point. We have to go verify the raw data and calculate the distance in this high-dimensional space between the query and this raw data points. If this distance is smaller than the BSF, then we update the BSF. And we proceed checking every single summary. So in this case, we find that the lower bounding distance between Q prime and C2 prime is greater than or equal to the BSF. Thanks to the lower bounding property, we can deduce that the distance between Q and C2 is greater than or equal to the BSF without even calculating it. And so C2 will not be a closer candidate than C1 and can be pruned, which means we do not need to visit it on disk. And we proceed until we check all the candidates and we return the final answer. So the skip sequential scans improve upon the serial scan because not all of the data is checked on disk typically. But we still needed to check all the summaries. So indexes, particularly tree-based indexes, have been successful in improving upon the skip sequential scans by organizing the summaries in a tree-based structure, where the internal nodes represent a summary of all the data that is stored in the underlying subtree, and typically the leaves point to the raw data on disk. So when a query arrives, a BSF is initialized to plus infinity, and typically a heuristic answer is returned by visiting one path in the index, going to the raw data that corresponds to the leaf, calculating the distance between Q and every single candidate in this leaf, and returning the smallest answer. Then search proceeds again from the root, and the node that is visited is added to a priority queue. The nodes with the lowest lower bounding distance have the highest priority. So the distance between Q, the summary of Q, given the node summarization, the current node summarization, is calculated. Then the distance between this summary of Q and the node is calculated. This is the lower bounding distance. Similarly to what we have seen before, this lower bounding distance is compared to the BSF. And if it is smaller than the BSF, we cannot prune this node. Okay, so we add its children to the queue. This is a priority queue. If node 2 is first in the priority queue, it means that it has the lowest, the distance between Q and the internal node 2 is smaller than the distance between Q and the node number 3. So we dequeue the node that has the smallest lower bounding distance. In this case, it is node number 2. And we continue. We compare to the BSF. And if we cannot prune, we have to add the children of node 2. We dequeue the node with the smallest LB. We calculate again the distance between the summary of Q according to node 5's summarization and the node summarization. And then we compare it to the BSF. And if we cannot prune, we have to add its children. In this case, the child that we added is leaf 2. The nodes that are represented in gray just mean that there is a subtree there. Trees are not necessarily balanced. So when we get to a leaf, we have to calculate the distance between the query and all the elements in this leaf, if we cannot prune it. And if there is a point in this leaf, such as the distance between Q and this point is smaller than the current BSF, we have to update the BSF. And we proceed by dequeuing the next element in the queue. In this case, it's node 4. And we find that the distance between Q prime, the summary of Q, to node 4 is greater than the BSF. So we can apply the lower bounding property, which tells us that all of the elements in this subtree, their distance to Q has to be greater than or equal to the BSF. And so processing the subtree rooted at node 4 will not improve the answer. And in fact, we can also stop, because we know that the priority queue has priority as the lower bounding distance. So the lower bounding distance of 3 is also between Q and node 3 is also greater than to the lower bounding distance between Q prime and 4. Now we will describe the main similarity search methods organized as a taxonomy. So similarity search methods can be either NG approximate, which means they provide no guarantees, or delta epsilon approximate, which means they provide delta epsilon approximate guarantees, where delta is between 0 and 1 and epsilon is greater than or equal to 0. When delta is strictly less than 1, the methods are called probabilistic. And when delta is equal to 1, delta epsilon approximate problems become epsilon approximate. A special case of epsilon approximate problems are when delta is equal to 1 and epsilon is equal to 0. These methods are called exact. In a previous experimental evaluation, the exact techniques were compared from different literature. And in a recent experimental evaluation, the approximate techniques were proposed. I'll do this part. Okay. Similarity search methods are represented in this following taxonomy. They can be categorized as either NG approximate, which means they return answers without any quality guarantees, or delta epsilon approximate, where the result is within distance 1 plus epsilon of the exact answer with probability delta. Delta is between 0 and 1, and epsilon is greater than or equal to 0. When delta is strictly less than 1, the methods are called probabilistic. When delta is equal to 1, the methods are called epsilon approximate. In a special case where delta is equal to 1, epsilon is equal to 0, the methods are called exact. An experimental study published a couple of years ago has compared the exact techniques from the data series and high-dimensional community. And a subsequent study has compared the approximate techniques and proposed extensions to the data series techniques to make them support all flavors of search: NG approximate, epsilon approximate, and probabilistic search. We will now cover the data series indexing process. So, one popular technique in the data series community is the DS tree. The DS tree is based on the EAPCA summarization, which itself is based on the APCA representation. In APCA, a data series is represented with variable length segments, such as each segment is represented with a floating point value representing the mean of this segment. In EAPCA, extended APCA, a segment is represented not only with the mean, but also the standard deviation. In DS trees indexing, each node in the index contains the number of vectors, segmentation of the node, and a synopsis. The tree is not balanced and is a binary tree. The leaf nodes store the row vectors. Another popular technique in the data series similarity search is SFA, or Symbolic Fourier Approximation. SFA represents each real-valued series with a string. An SFA is composed of approximation using the Fourier transform and a technique called multiple coefficient binning. Since symbolic representation is a character string, these representations can be used with string algorithms and data structures, such as prefix trees, bag of words, Markov model, or string matching. In addition to the DS tree and SFA, popular indexes in the data series similarity search community are based on Isaacs. The Isaac summarization that we described earlier. And as we have said, the Isaac summarization is bitwise. It allows us to represent different segments of the same series with a different number of bits, and this is what enables a small memory footprint, a hierarchical organization of the time series in the form of a tree, and fast bitwise operations while traversing the tree. This slide shows an example of an Isaac index, where each inner node contains the Isaac summarization of all series below that subtree. Leaf nodes also contain or point to the raw data series, so that we can remove false positives during query answering and get exact correct answers for similarity search. Leaves have a fixed capacity, and once this capacity is exceeded, a leaf is split into two children by selecting all the segments and augmenting it by one the number of bits that represent that segment. Please also note that the root of the index has more than 2 children. In fact, it can have up to 2 to the power w children, where w is the number of segments. The Isaacs index is built top to bottom and is a non-balanced index. The Isaacs 2 plus index is a newer version of the Isaacs index that supports bulk loading. The main ideas are that, first, it gathers in main memory as many series from the input as possible that will end up in the same leaf, and then it issues sequential discrete writes to materialize the corresponding leaves. Second, it handles separately the summarizations and the raw data of each data series so that operations are executed faster, using only the necessary data. And third, it applies an optimistic policy, assuming that the first leaf where each series gets into will never get split. These strategies result in the Isaacs 2 plus building almost an order of magnitude faster than the simple Isaacs index. The Adaptive Data Series Index, ADS+, is an adaptive version of Isaacs 2 plus. It represents a novel paradigm for building a data series index, starting to answer similarity search queries before the entire index has been built, while guaranteeing correct results. So this leads to a significant improvement, up to 7 times faster, for the time needed to answer the very first query using the index. The main idea is to build a high-level in-memory index based only on Isaacs summarizations and very large leaves, and then refine the leaves and bring the raw data into the index only when accessed by some query. This slide shows the ADS index when it has finished the first phase and is ready to answer queries. You can see that the leaves are large and they point to the raw data in the original file on disk, which permits the index to finish this phase quickly. In order to answer the query fast, the splits are further done on the leaf that is needed by the query until the leaf becomes small enough and the cost for reading it is minimized. The raw data is then brought into the index and the leaf is materialized with the raw data. So this approach ensures that the next time a query needs that particular leaf, it will find that the data is already there and the query will be much faster. Moreover, it's not necessary to spend time building a portion of the index that is not needed by the query workload. So overall, the query answering time is faster. Following the Isaacs 2 plus and the ADS plus indexes, several other Isaacs-based indexes were developed. Coconut is the current state-of-the-art index for limited memory devices, that is, devices where the memory is significantly smaller than the dataset size. It is also the first scalable data series index that is built bottom up. This is made possible thanks to Influx. It is an Isaacs summarization that is sortable. Note that sorting sequences or their summarizations is not straightforward because the sequences can be very similar in the first points and very different in the rest. This means that a sorted index or a sorted order should take into account all the points in the sequence in order to place close to each other in the sorted order 2 sequences that have the low distance between them. Coconut proposes such a solution using a space filling curve on the embedded space of the Isaac summarization of the series. And this results in an index that can be built bottom up, bulk loaded, and densely packed. Moreover, It can exploit single-dimensional indexes such as the B+ tree. Coconut has also been extended to operate on LSM trees, which are adapted for online operation. So Coconut LSM is the first data series indexing solution for similarity search in streaming time series. It allows users to efficiently index and answer similarity search queries for ad hoc windows in the past. So it is able to answer queries such as find sequences similar to this pattern that have occurred in the stream, for example, last week or last month. Ulysses is another index based on Isaac's summarization. It is in fact a single index that can support variable length similarity search queries for a wide range of lengths, ranging from a few hundred to a few thousand. The idea of Ulysses is that it indexes many subsequences of a series. Conceptually, what it does is that it considers each individual subsequence. It groups these subsequences and computes an envelope representation that contains them all. Then, each node in the index stores the Isaac summarization of the envelope of all these subsequences. And this enables Ulysses to answer variable length queries orders of magnitude faster than the other approaches.
So we will now discuss the data series indexing techniques that are parallel and distributed. An interesting observation here, if we take a close look at the ADS computation cost, is that 60% of this cost is CPU. And what this means is that there is lots of potential for improvement when we use parallelization and distribution. So one technique that takes advantage of this is Paris Plus, parallel indexing of sequences. Paris Plus is a solution for SIMD, single instruction on multiple data, multi-core and multi-socket architectures. It completely masks out the CPU cost during index creation, which means that all the cost that the user actually perceives is the disk cost. And this is true for both hard drive and SSDs. Paris Plus answers exact queries in the order of a few seconds on 100 gigabyte datasets, which makes it up to 3 orders of magnitude faster than single core solutions. And what this means is that, for example, if we consider some complex analytics tasks like KNN classification, this means that we can get improvements that make the difference between solving this analysis task in a matter of a few hours rather than several days. So now this kind of techniques have a significant impact on real applications. So let's see how Paris Plus achieves these improvements. For index creation, so in this picture, everything below the red line is disk and above the red line is main memory. So for index creation, we have a coordinator worker that reads data, raw data from the disk. It uses a double buffer to store this data in memory, and then creates index bulk loading workers, several of them, which read as input the raw data, they compute the Isaac summaries, and then they insert these Isaac summaries in the receiving buffers. There is one receiving buffer for every child of the root of the index. Then at the second phase, the coordinator spawns index construction workers. Each worker works on a single receiving buffer, and each worker then builds the corresponding subtree of the index. When some worker finishes their job, then they can jump to another receiving buffer and process that and grow that part of the index as well. In terms of exact query answering, we start Paris Plus starts with an approximate query, which means that it goes down the most promising path of the index. It visits that leaf and computes the first best so far answer. And then we have a set of lower bounding computation workers, which compute, which calculate lower bound distances and generate candidate answers. So candidate answers are only those whose lower bounding distance is less than the distance of the first best so far. So in doing this operation, we have to compute a very big number of lower bounding distances, and we do this using SIMD. So I will not go into these details, but this operation actually doing this operation in SIMD is almost 3.5 times faster than doing it in single instruction, single data. And then, as a last step, we read the raw data and verify which of the candidate answers is the best answer. MESI is an in-memory solution that uses SIMD multi-core and multi-socket architectures. The index creation algorithm of MESI achieves to balance the workload of the different workers and also minimizes synchronization cost. So this is achieved by a more careful allocation of work to each worker. The exact query answering algorithm, in this case, since we are in memory, is different than in Paris, and the goal of MESI is to minimize the number of lower bound and real distance calculations. With MESI, we have exact query answers at interactive speeds. So in about 50 milliseconds on 100 gigabyte data sets, which makes it 11 times faster than competing approaches in memory. So let's see how MESI achieves this, and let's focus on query answering. So query answering is different than what I described earlier with Paris. So we once again start with an approximate search to get the first best so far. So this is a very fast operation which doesn't make sense to parallelize. And then in a second step, MESI uses a set of priority queues where we store all the leaf nodes that cannot be pruned. And then, as a second step, we process these priority queues once again in parallel, and we first calculate lower bounding distances for each series in each of the leaves that are in these priority queues, and only then move on to the calculation of the real distances in order to produce the final answer. So the reason why we end up having a smaller candidate list, so a smaller number of lower bound and real distance computations, is because now we are in memory, and we actually use the tree to search the space and prune candidates that cannot be part of the answer. This was not true in with Paris. Another solution that belongs in this area of parallel indexes is SING, sequence indexing using GPUs. And this is once again an in-memory solution that exploits SIMD multi-core, multi-socket, and GPUs. So in this case, we have a new exact query answering algorithm that uses a CPU-GPU collaborative framework, and also a GPU-friendly lower bound distance calculation algorithm. So once again, we are at the interactive speeds, this time at 32 milliseconds for 100 gigabyte datasets, and this makes it 5 times faster than competing approaches. So an interesting observation here is that using, at the first glance, using GPUs to do data series similarity search is a natural solution. So GPUs are typically part of modern hardware. They offer massive parallelization opportunities, and data series operations are massively parallelizable. However, observe that GPUs have limited memory size. So modern GPUs commonly have around 12 gigabytes of RAM, and this means that they are much smaller than the raw data, than our data series collections that we want to analyze. They have slow interconnect speeds, which means that we cannot pay the cost of moving raw data in and out the GPU at query answering during query answering time. And lastly, the GPU cores, the streaming processors, are not so sophisticated, so they cannot run easily complex operations on complex data structures, support branching the same way that CPUs do. So all these limitations have to be taken into account when designing a solution that uses GPUs. So of course, these trade-offs will change as GPU memories and interconnects advances. Now, the way that SING performs query answering is that it offloads most of the lower bounding distance computations to the GPU. And the reason for doing that is because we can fit the ISAC summaries in the GPUs. Now, SING also tries to reduce the number of lower bounding distance computations that the GPU will perform by doing a pre-filtering using the ISAC summaries of the index tree. And then after the GPU computes these lower bounds, in this case, as I said earlier, we also have a GPU-friendly algorithm for computing these lower bounds. The reason for doing this is because traditionally for these lower bounds, we need to store a table with the ISAC's breakpoints, and storing this table, handling this table in the GPU is not easy. So instead, we approximate these breakpoints with a function, and then the GPU is using this function to compute the breakpoints. So this makes this operation about 10 times faster than using the traditional breakpoint table in the GPU. The reason why this is so much faster is because when we use the breakpoint table, these tables have to be stored in the L1 cache of the GPU, which is not as fast as the registers of the streaming processors. Right. So this is how Sing basically works. Now, DB Isaacs, the distributed partition Isaacs is a solution for distributed processing using Spark. DB Isaacs balances the work of the different worker nodes based on partitions that are divided using uniform groups, and this is achieved by doing sampling on the raw data, and then reasoning on the sample on what is the best way to partition the entire data set. So this picture shows this process where we have here in the red boxes the different nodes that on which we distribute the data set. So DB Isaac speeds up query answering. Exact queries are answered by all nodes through parallel query execution. Approximate queries are answered only by a single node, the most promising one based on the distribution on the partition, on the data partitioning that we have done. And in this case, we achieve parallelization in the workload execution. So this picture summarizes the Isaacs index family. And you can see the different functionalities that are supported from the different Isaacs indexes, as well as how each index inherits properties from previous ones. Now, TARDIS is a solution for distributed processing on Spark once again. It is based on the Isaacs transposition representation, which transposes the matrix of Isaacs words of the same cardinality and represents them as strings. So this is how this looks like. This is a traditional Isaacs word, which can be represented as a matrix, and then the transpose of this matrix can be transformed into a sequence in hexadecimal. And it is this sequence then that we index using the SIG tree. So the index now is an index where each node has a fan out of the number of words in one summary of a subsequence. And the interesting thing here is that as we go from the root to a leaf, we have nodes with increasing cardinality. So each parent is a prefix of each child. So in this case, we have a centralized global index plus distributed local indexes that also include the raw data. And the global index is basically constructed bottom up. So the data are already on the different nodes. And by sampling these nodes, we compute statistics that are used to build the global index. So this is how this looks like, where the global index is on a master node, and the worker nodes contain the local indices. And for query answering, the query uses the global index to identify the most promising partition, and then in that partition we search the local index to identify the most promising answers. So TARDIS supports approximate KNN queries as well as exact match queries. So exact match queries are queries where we want to identify, we want to check if our dataset contains exactly the same sequence as the query sequence. KV-match is a solution for distributed subsequence similarity search. So in this case, we are looking for a short query inside a very long series. And KV-match supports epsilon range queries and exact answers for constrained epsilon range queries. So epsilon range queries are queries that use the constrained normalized subsequence matching, which is essentially a constrained similarity search. Intuitively, it's Z normalization with constraints on the degrees of amplitude scaling and offset shifting. So this means that the user can control how much scaling and shifting should be allowed. And basically, the usual normalized subsequence matching is a special case of this CNSM. Now, with KV-match, the index creation works by sliding a window on the input series and producing ordered rows of key value pairs, where a key is a range of mean values and a value is the set of sliding windows whose mean values fall within the key. So within this range of mean values. So this picture shows how this operation works, as we have different sliding windows that for which we compute the mean values. We produce this key value table, and this key value table can be stored on HBase. For query answering, we query for a query Q and corresponding subsequence S. We have to segment Q, and then for each window Qi and subsequence Si, the filtering condition is that S is a candidate only if all the mean values of S fall within the corresponding interval of low and upper mean values. So we use the index to generate a candidate set of subsequences, and then we have to verify which of these candidates are correct answers by looking by computing the real distances on the raw data. L-match is an improvement of KV-match, where instead of sliding a window on the series in order to build the index, with L-match we slide a window on the query. And this means that the index is more compact and it's easier to build. And the operations are naturally parallelizable since we have no data window that is split between different nodes. And in this case, this is the picture. So we have disjoint windows for building the index on the long sequence, and we have a sliding window on the query. So compared to KV-match, L-match is slightly slower, but it's 10 times smaller. So it pays off. Finally, ParSketch is a solution for distributed processing. It uses Spark. It represents series using sketches based on the Johnson-Lindenstrauss lemma. So each series is represented by a set of different sketches. And then these different sets of sketches are distributed in different nodes on the cluster. Now each node then builds a grid index, and Similarity is computed by checking how close some candidate answer is to the query. So originally this method was proposed for epsilon range queries, but it can also support approximate queries. and it performs very well for high frequency series. So if there are any questions.
So we have covered a number of techniques that support data series similarity search, and in the next coming slides, we will compare and contrast some of the popular techniques. In fact, over the last 3 decades, a number of approaches have been proposed, but they were never compared against another extensively until a recent experimental comparison, which evaluated the state-of-the-art techniques based on a uniform experimental framework, using 2 different types of hardware, a hard disk drive machine and a solid-state drive machine. Datasets are ranging in size from 25 gigabytes to 1 terabyte, real datasets and synthetic datasets, real datasets from different domains, neuroscience, seismology, astronomy, and deep network embeddings, query workloads that range from 100 to 10,000 queries, and also queries of different difficulty. Wall clock time was used as a performance measure, but also time-independent measures such as the number of disk accesses, the footprint, the pruning, the tightness of the lower bound, and other criteria. All of the methods that were compared were built on the same implementation framework to guard against implementation bias. So all the techniques that were not originally built in C++ were re-implemented from scratch. The procedure is that in the first step, all of the methods are parameterized individually. Once the optimal parameters are determined, each method in step 2 is evaluated against some criteria. The best methods are then selected to be evaluated on additional criteria. So how do the methods compare in terms of indexing time? In this plot, you can see on the x-axis the dataset size, on the y-axis the total time in hours. The red dotted line indicates the memory size. So all the datasets that are to the left fit in memory, and the ones that are to the left fit in memory, and the ones that are to the right fit on disk. And the methods that were compared are the ADS plus index, DS3, ISAX2+, SFA, an optimized skip sequential scan called the VA plus file, and an optimized sequential scan called the UCR suite. We can observe that ADS plus is the fastest across the board, and the DS3 index is the slowest to build. How about query answering? Answering 100 exact queries is fastest using the VA plus file in memory and the DS3 on disk. How about when the indexing time is combined with answering a large number of queries? We actually extrapolate the cost of 100 queries to 10,000. And the verdict is that in memory, the VA plus file is still the fastest, and the DS3 is fastest on disk. We run another experiment, which is to vary the length of a series while keeping the dataset size the same in terms of gigabytes, to specifically test for the effect of data series length. Methods that use summarizations still use the same number of dimensionality for the summarization. In this case, it was 16 segments. We can observe that all the methods, or most of the methods, have steady performance, except 2 methods, which are the VA plus file and ADS plus, that actually gets faster with increasing length. So remember that the dimensionality in the reduced space is kept constant. So we only increase the dimensionality in the original space. And the reason why these 2 methods are faster is because they are skip sequential methods. So by keeping the dataset size the same and the series longer, we have fewer series in the dataset. And so both of these techniques make a smaller number of random accesses. This study led to some unexpected results. In fact, some methods were shown to not scale as expected, or actually not scale at all. The study also brought back to the spotlight two older methods, the VA+ file and the DS-tree. The re-implementations of these techniques actually outperformed by far the original ones. The study also demonstrated that optimal parameters for some methods are different from the ones reported in the original papers. And I think one of the most unexpected results is that the tightness of the lower bound was shown to not always predict performance. Let's see how. So first, what is the TLB? The TLB is a measure of the quality of the summarization. The higher the TLB, the better the summarization is. So it is the ratio between the distance of the query and candidate in the reduced space to the distance of the query candidate in the original space. And this value is between 0 and 1, where 0 is the worst and 1, a TLB of 1, is the best value. A TLB of 1 means that search can be conducted in the reduced space without loss of any accuracy. But this does not happen in practice. In practice, the TLB is strictly less than 1. So let's see. In this plot, we have the data series length in the x-axis. Let's pick length 256. The dataset size that was used is 100 gigabytes. The query TLB is shown on the y-axis. And here we have, in these boxes, the lines indicates the median TLB for all the queries that we run. And we can see that the DS-tree, which is shown in light green, has the same median TLB as the ISX2+. So the conventional wisdom had it that both of them will have equal performance. But we show that, in fact, in this plot, this is not the case. So for the same dataset size, which is also 256 length series, the DS-tree is much faster than the ISX2+ index. And remember that there is no bias here because it's the same data and the same implementation framework. And in fact, the reason is that the TLB is a good indicator of performance, but it is not the only one. Another characteristic is how well the indexes cluster the data together. A few insights were gathered from the study. In particular, that the results are sensitive to parameter tuning, to hardware setup, to the implementation, and to workload selection. Results identify methods that would benefit from modern hardware.
Hello everybody, this is Kostas Zoumpatianos, and now we're going to talk about time series management systems. Now, there are many ways that people have been using in order to store time series in the past. Those include not only the file system, but also relational databases, specialized time series databases, as well as ArrayDBs. In terms of the file system, multiple different formats have been used depending on the application and the domain. For example, in astronomy, it's very common to use FITS files and HDF5 files, while in seismology, people have been using SID, MiniSID, ASCII files, and GeoCSV files. Finally, in biology, which is a mass producer of time series data, people have been using BEADS files, WFDB files, EDF files, and FASTA files. In finance, it's very common to move data around in CSV files, while in engineering and physics, HDF5 and NetCDF files are the standard. Finally, in data science, people have been using CSV files, TSV files, XLS files, and Parquet files in order to store and process and load their data from. Now, in terms of database management systems, there has been support for time series from very early in the times. One of the first systems that supported time series was Illustra, which then became the Informix database, which is now part of IBM. Now, in this system, users have to define a time series subtype which has a datetime as the first column in the definition. Then they can encode both regular and irregular time series, which means fixed or variable intervals in which the timestamps are being measured. And they can also describe metadata, and there's support for multiple analytical queries such as running aggregates. They have the ability of like getting previous and next values, and also horizontal and vertical mathematical operations. In academia, the SEC system was one of the first systems that talked about storing and retrieving time series. So this was built on top of the storage engine, and it introduced a custom time series data type. Now, on top of that, various time series operators have been implementing like order, correlation, and so on. So this system was proposed as early as 1995. And also other commercial systems have implemented time series functionality since then. So for example, Oracle introduced time series functionality in the 8th version, which is now merged in the main product in the form of time series analytic functions. Now, the problem is that most people still use the BMSs only for like storing and retrieving time series, and all like more, let's say, like heavyweight analysis is still performed externally in systems like Python and R. Now, there are multiple time series systems that have been built from scratch in order to support this data type. These include Influx DB, which uses a custom storage format and the custom like data structure, which is called the time structured metric. Timescale DB, which is built on top of PostgreSQL and includes some kind of temporal partitioning. Beringay, which is a system from Facebook, which stores time series as compressed arrays on disk. And also Druid, which stores metadata on DBMS, but also stores time series in a custom format on HDFS or S3. Prometheus is also a time series specialized system, which also has its own custom file format, which is the DSDB format. CrateDB also has a column-oriented custom format, while IoTDB the same as we've seen earlier on. There's the TS file, which also includes compression and stats. OpenTSDB stores time series in HBase, while QuasarDB uses RocksDB as a backend. And there's also like big players that are now starting to implement time series functionalities, such as Amazon TimeStream, which still we don't have lots of details on how they're storing data. Now, another option for storing time series is array databases. So those include systems like TileDB, Rastaman, and SciDB. Now, TileDB uses a custom log structured storage format. Rastaman sits on top of existing database management systems, and SciDB has a completely custom storage layout. Now, we talk about like storing time series, but what are actually time series? So time series are sequences of recordings that can have varying starts, but also they can have varying ends, varying lengths, and also the sample rate at which the measurements are taken can be regular, like fixed, or irregular, and also they can differ across different time series and within time series. Now, apart from like the sequential attributes that we measure as time series, we also have non-sequential attributes which are attached to time series. So these most of the times are called also called tags. So for example, you might want to tag this time series saying that this belongs to sensor 1, and this is like in country Italy, and so on and so forth. Now, in terms of storage, how do we actually store this kind of tables? So there are two options in that regard. One is the collapse design and the other is the expanded design. And let's take a look at what those are. So in the collapse design, you treat each time series as a single record. So for example, you have a new specialized data type, which is called time series, that encodes all the sequential information. So this is the way that is chosen the Predator academic system. This is the way that is chosen in Informix, and also this is the way that is stored in like the Nestor database, which is our own experimental system. Now, the idea there is that you have this, as we said, specialized data type, and on top of that, you implement specialized UDFs. When you store this data type, you can have like your own like specialized compression algorithms. You can choose to inline this data type, this large object within its row, or like put a reference to an external store. And in detail, what they did in the SEC project, for example, was that they used to represent each time series as one SOR, a large object per series that contains one sparse array per series. So they used as a backend for this system the SOR storage engine developed at Wisconsin and then developed also by EPFL. And this proved to be like a very efficient implementation. Now in Fourier they also have like a similar design, but now they can also like inline data within each row if the time series are below 1,500 bytes. But if they are like above that threshold, they reference an external container where each time series is sorted by time. Now the expanded design is essentially a denormalization of this idea. So you, for example, create one new record per timestamp, and then you replicate your like metadata as many times as the timestamps that you have. So this is a design that is very commonly used in practice, also because it's very simple to describe. And in order to have like still have like efficient performance, people have been doing like partitioning and also have been building like specialized indexes on top of this layout in order to still be able to efficiently navigate this data. Now in Teradata, which follows this design, one can specify that the columns that are sequenced on this timestamp, and the system internally can index data and allow for fast retrieval. In timescale, the same thing happens. You can create like a hypertable above an existing table, saying that this table is has to be sorted by timestamp and also partitioned by timestamp. Above that, of course, because we have lots of repetition in the metadata, we can either compress the data or even encode them using inverted indexes. And this is common in systems like InfluxDB and Druid, where in Druid, for example, we have one bitmap per value per metadata column. And this, especially for columns with low cardinality, makes it very efficient to do like tag-based queries. Now, what about clustering? So assume that we have like this big expanded table. Should we like sort cluster data by like a sequence ID, or should we cluster data by globally by timestamp, like sort all time series by timestamp? So it's not clear. So it depends on the workload. So if you do heavy filtering on positions and you're accessing lots of series, you might want to cluster your data position first. While if you do heavy filtering on series IDs and you're accessing lots of positions, you might want to access your data sequence first. And the expanded design gives you this kind of flexibility to choose how you want to cluster your data. Now, we also did a small experiment. We saw that, like, depending on how many sequences and how many positions you select, like a different clustering might be your optimal solution. Now, most existing systems, they sort the data by series because this is like the most common case where you want to access like one series at a time. Now, in terms of queries, one would wonder what kind of queries do people do on top of these like stored data. Like there's one category of simple queries, which are like simple selection, projection, transformation queries, which essentially given a collection of time series, you can select a subset of those time series. For example, I want like time series 1 that refers to a specific city, time series number 2, and time series number 3. And then I might want to look at some positions of this subset of time series, for example, from day A to day B. And on top of this, like a time range for a subset of the time series, I might want to be able to apply a function, for example, give me the average, or like give me a Fourier transform. Now, in order to like be able to optimize such queries, one can use, of course, like classic one and r-dimensional indexes, like all the layouts that we've seen, and it's trivial to do like to then like implement like queries like point get and range get and things like that. Now, one of the most interesting like types of queries are, as we've also seen earlier, the complex queries, the analytical queries, like for example clustering, frequent pattern mining, classification, outlier detection, this kind of stuff. Now, for example, clustering is when you're trying to find groups of time series that are similar. Classification was when you're trying to assign a label to a time series based on its shape, while frequent pattern mining is about finding patterns that are frequently appearing within and across time series. Finally, outlier detection is about finding time series that have patterns that are abnormal. Now, in order to be able to answer this kind of queries efficiently, one has to rely on A, specialized algorithms, and B, efficient similarity search, as this is the core operation of most of these algorithms. Now, let's take a look a little bit on how two popular systems work under the hood. Those are InfluxDB and TimescaleDB. So as we've also quickly said earlier, InfluxDB uses what they call a log structured merge tree. This is essentially an LSM tree variant which expects data to arrive ordered by time and then tries to partition them by distinct sequence. So essentially, it gets data that are globally sorted by time and splits them by sequence ID and still sorts them in time. In terms of schema, you have tags and fields. Tags are used to describe metadata, and fields are used to store the quantities that change over time. So, for example, like pressure and temperature. The type of queries that are supported by InfluxDB are like group by, which is only supported on tags at the moment, and joins on timestamps and fields, as well as selections, projections, and aggregations. And it also supports continuous queries. TimescaleDB doesn't have its own storage engine because it relies on PostgreSQL as its backend, and it partitions time series into multiple tables that form a single virtual entity called a hypertable. This allows for the compression of data, and this is something that Postgres does not do by default, so they have implemented that on top of Postgres. In terms of schema, tables are normal Postgres table, where one has to specify a specific time column in order to create a hypertable. For queries, we have full SQL support, with the addition of custom time series functions, such as first, last, histogram, interpolation, time bucketing, gap filling, etc. And it also as well supports continuous query. Now, in terms of challenges and open problems, now we're still far from having solved the problem of how to store and process time series. There are still several challenges in terms of usability, scalability, distribution, and even benchmarking. So these challenges derive from modern data series applications. Now imagine that we have a huge data deluge of time series at this point. NASA Solar Observatory produces about 1.5 terabytes of data each day, while the Large Synoptic Survey Telescope produces about 30 terabytes of data each night. The Human Genome Project contains 130 terabytes of sequences, while each engine of a Boeing jet produces 20 terabytes of sequential data each hour. Finally, data centers such as the data center of Facebook, they have 2 billion unique data series that produce about 4 million points per second. So we have big data there. Now, in terms of a sequence management system built from top to bottom, that would enable practitioners and non-experts to easily and efficiently manage and analyze massive data series collections. And by saying analyze, we mean also supporting advanced analytics. Now, our vision towards such a system, which has been proposed in Sigma Record in 2015, and in HPCS 17 and ICDE in 2018, has the following stack. You have data sequences. You should support you should have support for summarizations, a very well designed query language, specialized access methods, support for variable length queries, uncertainty, and also distributed processing, and also holistic optimization, which is a big part of having an efficient system. Now, about holistic optimization, as we said, there has been some work by Echihabi et al. In VLTP 2018, where multiple time series indexes have been compared in order to identify in which cases which index performs the best. And it turns out that it's not like a simple like choice. Like you have to look at the data characteristics, like your actual hardware, in order to identify which of the currently existing indexes works the best. Now, in order for choosing like the best method for a given data set, there has also been work by Lavchenko et al. Where they proposed a method to choose between DP ISACs and the parse kits based on the data parse spectrum. So the idea is that an industry standard representation, which is called ISACs, is less efficient than parse kits for high frequency data because it relies on the time domain in order to summarize data. So it does like piecewise aggregates, which don't work well when you have like very frequent changes. So in parse kits, if there's substantial power, at least up to the 30th coefficient, then best neighbor chooses it. Otherwise, DP ISACs is used. Now, the questions is how do these results extend to other data characteristics, more indexing methods, and how could you also take hardware specifications into consideration? And now a big part of like understanding how different like indexes behave and how different like indexes behave on different systems is also like having fair benchmarking. And there has been little work on that. Because previous studies have evaluated performance of indexing methods using just like a random queries that have been like randomly chosen for the data with or without noise. The problem with such random queries, though, is that you have no control on their characteristics, which means that you cannot properly evaluate summarization indexes. So what we need actually is queries that can cover the entire range from easy to hard. So in terms of like previous workload, there has been work that showed that previous workloads were mostly skewed towards easy queries. And this is the case across like multiple different data sets. Now, the problem is that if your all queries are easy, all indexes look good. Well, on the other hand side, if like all queries are hard, all indexes look bad. Now, what we actually need is methods for generating queries of varying hardness. Now, the way that the indexes for time series work is that you give them an example of a time series, and then they give you the time series that look most similar to this example. Now, in order to do that efficiently, they rely on summarizations. And then using these summarizations, they can compute a lower bound on the distance between the example query and all the time series in the database. However, this minimum distance depends on how close these, like similar these time series that exist in the database are to the given example to begin with. If you have lots of time series that are very similar to your example, your query is very hard because it becomes very hard to distinguish which one is the closest. While if they are very far away, the query is super easy because it's very easy to distinguish that like some of those are like closer to some others. Now, in order to be able to judge how good the summarization is, and essentially how good an index is, you need to have like the time series that spread the whole spectrum of like close to far, so that the worse your summarization is, the more data that you need to fetch. And the idea in the method proposed in KDD 2015 was the following: that you get like a data set, and then you densify this data set by putting the synthetic data in locations in the high dimensional space, which are sparse, which do not contain lots of like time series. So the experiment showed that this is a good idea. So if you take your original summarizations and you compute their quality by measuring what is called the tightness of the lower bound, this is the average ratio of the real distance versus the lower bounding distance over lots of like time series pairs, and then you normalize this from using the best performing summarization, and you also compute the effort that the indexes did using the specified benchmark as an input, and you also normalize this effort based on the best performing index. And then what happens is that essentially we see that the worse the summarization is, the more effort that it does. So essentially you can capture this like degradation of like summarization quality in terms of like actual work done by the index. And this is exactly what we want from like a good benchmark.
So in practice, this work provided the theoretical background for characterizing nearest neighbor queries for data series indexes, and also proposed a nearest neighbor workload generator. The problem with this method, though, is that it has very high time complexity, and thus we need new approaches that can scale to larger datasets.
We will now cover additional challenges and open problems in data series similarity search, in particular, the importance of interactive analytics, parallelization distribution, how data series relate to high-dimensional vectors, and how deep learning can be exploited in this context. So data series analytics is computationally expensive because of the very inherent complexity. While it may not be always possible to remove delays, a good idea is to try to hide them. The interaction with users offers great possibilities. For instance, providing progressive answers. A progressive answer is an intermediate answer that converges to the final correct solution. In a recent work, it has been shown that the time it takes for an algorithm, the data series algorithms, to find the exact 1NN is much smaller compared to the time it takes for the algorithms to finish execution and guarantee the correctness of the results. And in this plot, we can see different datasets, seismology, neuroscience, and deep neural embeddings. Each of them of size 100 gigabytes. The gray bars indicate the time it takes for the algorithm to finish, and the blue bars indicate the time it takes for the algorithm to find the actual 1NN. We can see that these algorithms find these answers much faster, much early in the process. In the graph to the right, we can see that for the seismology dataset, for specific queries, let's take, for instance, the yellow one, it takes only a few steps for the algorithm to find the actual answer. In this case, it took the algorithm, we use Isaacs2+, it took the algorithm only a second to find the correct 1NN, whereas the exact search algorithm has to execute for an additional 99 seconds before it completes. A recent work has provided guarantees on top of these intermediate answers. So given a query, an initial estimate is provided with the probability that this 1NN answer is the correct one, and also an estimate of the time it would take to find the actual NN. As the algorithm processes more data, the probability improves. In this plot to the right, the algorithm processed about 16,000 leaves using the Isaacs2+ index in about 16 seconds. Although the probability is only 98%, this is actually the exact answer. And the final result, however, takes 75 seconds and needs to process an order of magnitude more leaves. So this opens several exciting research problems at the intersection of visualization and data management. At the front end, the need for HCI visualizations for querying and results display, and at the back end, the importance of efficiently supporting these operations. We have shown some parallel and distributed approaches that tackle the data series similarity search problem, but there is still room for improvement. So in addition to taking advantage of SIMD and multi-tier CPU caches, multi-core, multi-socket architectures, and GPUs, it is also important to leverage new storage solutions such as NVRAMs and FPGAs, and of course, scale across many compute clusters. Because the techniques are inherently parallelizable across cores and across machines. In particular, we need to propose methods for concurrent query answering. Instead of answering one query at a time, a query workload is answered in parallel. We need to combine multi-core and distributed methods and examine FPGA and NVM technologies. Moreover, it is important to minimize the total work, not only in terms of execution time, but also energy. And that challenge is more difficult. How do Heidi vectors relate to data series? Is data series similarity search and Heidi similarity search two sides of the same coin? So data series are multidimensional points, but there are specific types of Heidi vectors or Heidi data, because the dimensions are the neighboring dimensions are correlated, and the order of the dimensions is important. Several techniques were proposed for similarity search in Heidi vectors. In particular, LSH techniques, where SRS is one of the best methods, space quantization, where IMI is the best contender, and neighborhood proximity-based approaches such as K-NN graphs, or those based on navigable small worlds like HNSW. So how do these techniques compare to data series? A recent experimental comparison was conducted to evaluate these techniques, and it has demonstrated that data series techniques are the overall winners, even on general Heidi vector data. In this plot, the methods that are compared are the DS3, HNSW, IMI, ISAX2+, SRS, and the VA+ file. And it is important to note that this study did not only conduct an experimental evaluation, but also proposed extensions to the data series indexes to enable them to support NG approximate search and delta epsilon approximate search. So we can see that DS3 and ISAX2+ perform best. Higher to the right is better. On the x-axis, we have accuracy, and on the y-axis, we have throughput. In memory, HNSW is still the best contender in terms of throughput. Data series approaches also perform best for long vectors in memory and on disk. They perform the best for disk resident vectors. Please note that techniques such as HNSW are only designed in memory. So this opens up new applications and challenges, of course, for data series similarity search techniques. Deep learning can be exploited in the context of similarity search. We have just discussed that data series indexing can work for deep network embeddings. What is a deep network embedding? Deep network embeddings are learned with deep neural networks. In this deep neural network, the input can be a sequence, a text, an image, a video, or a graph, or another high-dimensional object, represented with the green circles. And the deep neural network learns an embedding in one of its hidden layers, shown with the blue circles. The popularity of learning these embeddings is growing. And the data series techniques have been shown to provide effective and scalable similarity search over these embeddings. Deep learning can also be leveraged to learn summarizations for data series. For example, autoencoders can learn efficient data series summaries. Deep learning can also be used to learn indexing structures and in the context of query optimization. Overall, we demonstrated that data series is a very common data type, that complex data series analytics are challenging. We argued for the need for a sequence management system to optimize operations based on data and hardware characteristics, while keeping these operations transparent to the user. We identified some exciting research opportunities, and we're ready to answer your questions.